Greetings everyone, this is Jeff Wilkerson, Professor of Physics at Luther College, and today this video is for the students in Engineering Science and Physics 150, and we're going to do a little bit of clarification, a little bit of simplification of the data analysis that we're doing for the simple pendulum that we've been looking at. And one of the things that we looked at was we said this was our expectation of what we might expect, how we might expect the period to depend on the length of the pendulum. And one of the things we're practicing here in our first foray into engineering and physics in college is thinking about ways to analyze data. And one of the ways we're going to do this is we're going to take the logarithm. We asked you to plot, I asked you to plot, I suggested to you that it was a good idea to plot the log of the period versus the log of the length. And we gave some generalized examples to show why this was useful. But let's dig right into the specifics here and use this, make sure we really understand this, what we're doing, so that we can use this concept as we move forward. And what we said was, okay, the log of t, let's do that this way. The log of t is going to be equal to the log of 2 pi g to the minus 1/2 L to the 1/2. And that's just our, we take the log of both sides. That's going to be fine to do. And the log of t, we'll be able to associate with y in just a second. But we also remember that the log of a times b, we've said, is equal to the log of a plus the log of b. And so we can say this is a and this is b. And so we can write this as the natural log or the log, whatever, base 10 log, doesn't matter what log you're using, 2 pi g to the minus 1/2, all the constants that are out there, plus the log of the length of the string, which you varied in this experiment, to the 1/2 power. This is our theoretical expectation, right? And so now we have a term that's all constants. We have this term, but we also said that the log of x to the n is equal to n log x. That's an identity that we remember. And so we look at that, we say, that's n log x. So we can take log of L to the 1/2 is going to be 1/2 log L. So we write this as 2 pi g to the minus 1/2 time plus 1/2 the natural log of L. But this is what we plotted on the x-axis. So now we have some constant here. What we plotted on the x-axis of our graph and what we plotted on the y-axis of our graph. And we think about this then as y is equal to mx plus b, or let's write it in the way we have it written right there, b plus mx. And x is that, and y is that. And so we have a b, we have an intercept, and we have a slope. We have a predicted slope and we have a predicted intercept, right? And we can test how close we got to that. We're working our way toward doing this more statistically, more numerically. We're going to be able to build confidence intervals and say with 95% certainty or 99% certainty, but we're not quite there yet. We're working our way that direction. And what we can say is we should be able to predict what the slope of our line is. So we plot this data, and we did a linear fit. And when we did a linear fit, we have the slope of the line and we have the intercept down here. And so we have the slope of the line and the intercept, and we've predicted what they should be. And what we want to do is compare that to our actual data. And so we have a measured slope. And so we can take the measured slope, the observed slope, minus the expected slope, the theoretical slope. And then we want to ask the question, well, are they close to each other or not? And your inclination is probably to say, yeah, they're close, but maybe they're close and maybe they're not close. That's an arbitrary. We don't really want to ask that question. It's really not a useful question to ask in that form. Close is an ill-defined concept. So what we want to think about is normalizing this to the uncertainty in those quantities. And the uncertainty we're going to write is the standard deviation, but that's the uncertainty in the observed. There's no uncertainty in the expected. That's a theoretical expectation, but there is an uncertainty in the observed, and that's one of the things we've been working on, is figuring out how to get the uncertainty in the slope and the intercept of a linear fit. So we have a slope in this, an uncertainty in this term, and an uncertainty in this term. We know what this term should be because we know what g is, and we know what pi is, and we know what 2 is, and so we can do the same thing for the intercept, but we'll just work with the slope right now. So what we're wanting to say is we have an expected slope that we can get from here. we have an observed slope that we got from our data, from our fits, and we want to extract the uncertainty from that linear fit. And when we extract the uncertainty, what we're really asking here is how many, let's just do that in absolute value terms, but to say how many standard deviations, this is a language we want to start to practice using, is to say how many standard deviations do our expected value and our observed value differ from each other. Okay, this is going to be a very helpful way to think about this for us going forward. So that's what we're asking. If your expected value is 1 and your experimental value is 0.92, you don't really have any sense of whether that's how close you got. The difference is 0.08, but if the uncertainty in the fit here is 0.02, 0.08 divided by 0.02 is 4, we would say we're 4 standard deviations away from the expected. And what we'll talk about down the road is that's actually quite a ways away. If we're wanting to think about did we confirm or did we not really confirm? We don't use that language. Did we falsify this? And the answer is yeah, maybe we did. But why? And we have to go back and look at our experiment and understand what's going on. But that's what we're doing. We're using this to pull out what we would expect the slope and the intercept to be, and then we're measuring that's the expected slope, for example. We do the exact same thing with the intercept, b observed minus b expected over the uncertainty in the values that we had right there, and to say how many standard deviations are we away. We're measuring the difference in standard deviations. We're measuring the difference in uncertainty units. So we're normalizing out the difference in the slope to the uncertainty in the slope. And we're saying how far away were we in those terms. So that's what we want to do. Walk your way through this and see if you can't do the data analysis for the pendulum this way, and then come ask me questions if you have questions.